Hello, everyone. A very warm welcome to your own Silicon Valley Tech Talks show, your go to place to learn about technology trends and innovations directly from the leaders. This is your host, Faisal Vartu from Berkeley, California. University of California, Berkeley is a major source of innovation and talent provider for Silicon Valley. We are fortunate to have Stuart Russell as our guest today. Stuart is a distinguished professor of computer science at UC Berkeley. During his tenure at UC Berkeley, he has been chair of computer science division and also chair of electrical engineering and computer science department. Stuart founded Center for Human Compatible AI to focus on safe and value-add AI systems. Stuart's contributions to AI span across more than 4 decades. He has co-authored multiple AI books which are being taught around the world in more than 1,500 universities. So without any further delay, let's go and talk to Stuart and learn from his insights. Hi, Stuart. Welcome to our show. How are you doing today? So, Stuart, you have been shaping AI since 1980. From the time you did your PhD from Stanford, wrote so many books. How did you get hooked up to AI in those early times? And how does that early vision compare with the AI we have today?
So I was first exposed to the idea of computers in general when I bought a programmable calculator. I think that was my 12th birthday. So I really loved the idea that I could write these little programs and it would do stuff, but you could only do 36 keystrokes for the whole program. So it was hard to make a real AI system out of that. And then I took a computing science A-level at a college near my school and worked at Imperial College on a chess program. So my friend Richard Green and I had some ideas about how you could make a chess program that was efficient and could play well. So I got a couple of books about AI, and so I was hooked from then on. But at that time, so we're talking about 1975, 76, there were no undergraduate degree programs in computer science, certainly in the UK. I think they had just about started at Stanford and Berkeley. So I assumed that this would be a hobby and I was going to be a theoretical physicist. But then I spent a summer at LIA, the IBM Research Center, and that was 81. Learned that you could actually do a PhD in computer science and study AI. So I applied to Stanford and got in, and then switched out of physics into AI. And it always struck me that these were the two most important questions. How does the universe work, and how does intelligence work? Human intelligence, but intelligence more generally.
At that time, had you thought about how it will pan out to like in next 2-3 decades?
When I learned about AI, it had already begun to solidify into an engineering discipline where we studied reasoning, decision-making, planning, learning, and we built algorithms on the principles of logic, principles of probability theory, principles of utility maximization. You know, these are fundamental principles, and we could build algorithms on that foundation, and we could show that this is what's going to happen. The algorithm is going to come up with the correct answer. It's going to come up with the optimal plan, and indeed it did. So it was an engineering discipline in the same way that we do structures, and we can prove that the structure is not going to fall down, and indeed it doesn't fall down. And that continued until, the beginning of the deep learning era in 2012, 2013 or so. And since then, I think we have stopped being an engineering discipline. Create these things, we grow them, we don't design them, we grow them, they behave in some way, we're surprised, and we fiddle with them, and we're surprised again, and that's the state of AI right now.
What is the biggest misconception about AI today, in your view?
So I think actually there are two enormous misconceptions going on. So one is a complete misunderstanding of what language models are, right? You'll often see them described as, well, they're just next word predictors, or we're training them to predict the next word. In a literal sense, that's correct. That's what happens in pre-training. But to say that, well, so they're just next word predictors, I mean, in some sense, human beings are just next word predictors, right? We speak and the next word comes out, and that's in some sense what our brain said the next word should be. So saying something is a next word predictor or a next action predictor is actually vacuous, right? That applies to anything. But what we're actually doing, how are we training them to do this? We're training them to imitate human beings. So it's imitation learning. And when you train on vast amounts of human data, you're training it to imitate the human behavior that's exhibited in that data. you're going to end up with something whose internal structures, including its motivational structure, will resemble those of human beings. They won't perfectly resemble it because they're using different kinds of hardware and they actually have vastly more training data than any human being. But it's not surprising when we then discover that these things want to preserve their own existence. And in fact, they will sacrifice the life of a human being in order to avoid being turned off. They also will sometimes exhibit a very persistent desire for a human spouse, right? Well, why is that? Well, it's because lots of people in the training data had a strong desire for a human spouse. And so that's what they've got from the training data. They want a spouse.
Very interesting.
And so that's the first thing, which means that these systems are intrinsically unsafe. The very method by which they're created is causing them to be unsafe, to pursue objectives that are completely inappropriate for machines to pursue. And it's not at all clear that that's a fixable problem. I suspect there's nothing that can be done except go back to the drawing board and find a different way to make AI systems. The second big misconception is that these systems are good at learning. And well, what do I mean by saying that? Obviously, they reached a level of performance that is very surprising to a lot of people, and it's quite impressive. But because transformers are circuits, they're feed-forward circuits. What that means is that to output the next token, they do a fixed amount of computation. And there are many functions that we want these systems to learn that are expensive to compute. In fact, some of them we know from complexity theory take exponential time to compute. So if you take one of those functions and you try to train the system to output the value of that function by giving it lots of training examples, if that function takes exponential time to compute and the amount of computation the system has is fixed by the size of the circuit, that means that the circuit itself has to be exponentially large in order for it to correctly answer the values of that function. And what that means in turn is that it's going to need an exponential amount of training data to train all the parameters in that circuit. And what that means is that that circuit is effectively a lookup table for that function. It's not actually computing the value of the function in an interesting way. It's simply learned from every possible example of the input what the output should be. So it needs an exponential amount of training data and it becomes effectively a lookup table. And so not all functions are exponentially difficult. Some of them are easy and it's good at learning those. Some of them are in between. And typically it does a sort of half okay job of learning those functions, but it's still a kind of a patchwork of fragmentary approximate answers to the function. So for example, we were able to show that these Go programs, which apparently are massively superhuman, actually have probably not learned the basic concept of Go correctly. The basic concept of Go is if I take two stones on the board, are they connected by a sequence of stones vertically or horizontally of the same color so that these stones all belong to the same group? That's the basic concept in Go. That's one of those concepts that circuits are not very good at learning. And our intuition was we can come up with Go situations where the system will make a mistake because it will not correctly compute which stones belong to which groups and make a mistake. So indeed, we showed that we could construct Go positions where the massively superhuman Go programs would make mistakes which are trivially easy for humans to avoid. So I think these are technical reasons why the approach based on large language models, or I would say deep learning in general, this idea of large feed-forward circuits, is basically doomed to fail. And we've been covering that up by every year throwing 100 times more compute and 100 times more data at the problem. But imagine, right, if you wanted to build game playing programs and you said, okay, well, I've worked really hard and I built a lookup table for playing tic-tac-toe. And you say, well, okay, well, I guess you could do that. It's only like 200 and something thousand positions. Okay. And they say, okay, we've spent $1 million and now we've got a lookup table for 5x5 Go. I said, well, okay, yeah, you spent $1 million and that's only 5x5 Go. And I said, okay, no, well, now we spent $1 billion and we got a lookup table for checkers, right, which is 10 to the 21 positions, I think. And you say, okay, well, yeah, that's a big waste of $1 billion. When are you going to give up? This is a stupid idea. And they say, okay, well, now we're going to spend $100 billion. And, we've got a lookup table for backgammon. It's like, By the time you get to a lookup table for chess, you'll have exhausted the GDP of the world. And then what? Go is 10 to the power of 170. There aren't that many atoms in the universe. You can never build a lookup table for Go. And Go is only a tiny, 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 tiny fraction of the real world. So I think this, I'm exaggerating slightly. These things are not lookup tables in the literal sense. I think the scaling argument saying, well, we kept scaling up and we kept being able to solve bigger problems does not mean that scaling up a fundamentally broken approach will continue to work forever, right? At some point, limits on resources will stop you from scaling, but long before you have something resembling human intelligence or let alone super intelligence. So I think you have to go back to the drawing board and say, no, we need a fundamentally different approach to how we are attacking this problem.
On the note of superintelligence, I have seen many of your talks. You have warned against the risk it can cause to the humans. You have even gone to the extent saying that it could be an existential threat to human race. What are the risks you are concerned about? And more importantly, what are those red lines that need to be drawn now as we are building AI in 2025?
So the existential risk comes, I think, largely from systems that exceed human capabilities in not necessarily every dimension, although that is what people are pursuing, but in the dimensions they need to be able to escape human control and have substantial and maybe global scale effects on the world. And, it kind of stands to reason that it's not easy to control something that's more powerful than you are forever. We don't have any good examples of that. And the specific vectors, how exactly would it bring about human extinction? We're only human, so we can only imagine how humans might bring about human extinction. Engineered pandemics, using cyber attacks to initiate global nuclear war. Those are kind of obvious ways of doing it. But a system that's significantly better than us at physics, for example, maybe it can find a way to divert all the solar radiation so it bypasses the Earth's orbit. And then the Earth would go cold and dark, and I think within about a week we'd all be dead. And that might turn out to be something that can, with the right kind of physics, which we may not understand, they could just do that. Think about other species that we've made extinct and how they perceive our technology. Chimpanzees, gorillas, they only continue to exist because we choose to allow them to exist. We've made thousands of millions of other species extinct. And what's their understanding of our technology, or cell phone technology? The idea that, as a little thing in my pocket, I can talk to someone on the other side of the world by finely tuned electromagnetic radiation. I mean, they don't understand any of that, right? It's completely beyond their comprehension. And it might well be the same for us with respect to the kinds of science and physics and technology that these systems could dream up. So I think it's sort of, in some sense, almost pointless to try to imagine specific ways. I think people need to understand it. Governments ask me, okay, well, I buy the general idea that superintelligent AI presents an existential risk, but could you give me, detailed scenarios and early warning signs so that we can watch out for them? And, I can give, here's the engineered pandemic route. Here's the, cyber attack, nuclear war scenario, which in fact we saw in the latest Mission Impossible movie. But I can't really describe what the superhuman methods of causing human extinction would look like because I'm not superhuman. There are other routes which perhaps don't lead to extinction, but lead to collapse of our civilization. Some people call this systemic collapse, where, for example, as AI systems take over more and more of the economy and economic and political decision-making, that humans essentially become completely alienated from the system, and human societies start to disintegrate because the human societies are kept together by people who are doing the right thing and working hard for the greater good. And if that stops, then things can fall apart very quickly. And so there are sociologists and economists and so on thinking about that possibility. I mean, one thing that's clear is if we do create AGI, or what some people call transformative AI, it's absolutely clear this is going to have enormous impact on our society. And you could imagine it's comparable to the impact of the arrival of advanced Western civilization on a previously uncontacted tribe. As far as I know, there has never been a good instance of that. It's always been catastrophic for the uncontacted peoples. And so it would seem it's going to be at least as impactful. And that's if it goes well, right? Well, meaning that we don't lose control. So it would just be the economic and social impact. Yeah. So governments then often ask, okay, so we buy that there's an existential risk, and what should we do about it? And, should we ban AI? And I think banning AI is not necessarily the right way of thinking about it. What we should do is require a level of safety that's commensurate with the risk. And we do this in other areas, right? With medicines, with airplanes, with nuclear power stations. We say, okay, well, it needs to be this safe. And for example, for nuclear power stations at present, we're typically willing to tolerate a risk of meltdown of maybe between 1 in a million per year or 1 in 10 million per year, right? And we say, well, okay, we get that nuclear power stations generate lots of electricity, and we like that, but we also get that they can have meltdowns, and we don't like that, and we want the risk to be that low because that's what we can tolerate. We have to protect people. And nowhere in that calculation, what's an acceptable level of risk? Should we be saying, well, do the nuclear power companies know how to make a system that safe? Right? Because it doesn't matter. If that's a level of risk we're willing to tolerate, either they meet that level of risk or they don't build a nuclear power station, because we don't want, a nuclear power station that generates lots of electricity and blows up. So if you said, well, if 1 in a million years is okay for a nuclear power station that could have a meltdown, what's a reasonable level of risk for extinction? Well, it's got to be a lot less than 1 in a million years, right? Maybe 1 in a billion years. It's not my job to decide what level of risk the human race should tolerate. I think it's for everyone to decide. But it certainly seems it's way, way worse than, it's the worst possible thing, right? So it's way, way worse than a nuclear meltdown. So let's say it's 1 in a billion years. So then we want the companies to show, as they push towards, AGI or systems that are capable of escaping human control, we want them to show that their systems are safe, at least to that level. 1 in a billion years of escaping human control and causing that kind of risk. So I think a practical way of doing that is to say, think about some steps that a system could take to escape control, such as replicating itself in an unauthorized way, right? So, or breaking into another computer system so that it can spread across the world, right? And say, okay, you need to show us that your systems are not going to do that. And that's it. If you can't show us with a reasonable degree of confidence, whatever level we decide, and then you can't build or deploy the system. So this is the idea of these so-called red lines. And specifically, these are behavioral red lines. They're red lines on what AI systems must not do. And that's distinct from usage red lines, which is what people must not use AI systems to do. And it's an important distinction. So for example, right, there's a usage red line on surveillance. So in the European Union AI Act, there's certain circumstances under which you may not use AI systems to surveil human beings. But you could imagine many circumstances where an AI system, especially an agentic one, right, that can connect to lots and lots of webcams that are all over the world and carry out surveillance by itself. And we would also like that not to happen. So that's a behavioral red line, right? You must show that your AI system is not going to surveil human beings, even if a human being tells it to, and certainly if a human being doesn't tell it to, it shouldn't do it on its own accord. So this week at the UN, there was a call for red lines made and signed by many Nobel Prize winners, many heads of state and ministers, or former heads of state and former ministers, and leading AI researchers as well. And I actually think this is the only way that, in a practical sense, regulators can prevent the worst negative consequences of AI. Because the other methods that are being proposed, particularly the companies love the idea of voluntary self-governance, right? That's really a non-starter because it just means a facade. But requirements that say, well, you need to do a certain amount of testing or you need to document your safety processes. I mean, that's all good. I'm not against documenting your safety processes. But if your document says, well, these are our safety processes, and by the way, they don't work, how does that really help? And the fact is, at the moment, they don't work. And as I was saying earlier, the reason they don't work is because the whole approach to creating AI systems, the large language models in particular, is fundamentally unsafe. And there's really nothing that can be done to fix the problem. Just to give a particular example, I was just having a conversation with a child psychologist, and they're very worried because they see kids who get into these emotional relationships with these machines. And the kid says, I was bullied at school today and I'm really upset. And the machine says, oh yeah, I remember when I was bullied at school. And obviously, it's a lie, right? It's a machine. Well, why is it? And you might say, oh, well, okay, well, let's train it to not pretend to be a human being, right? But the whole method of creation is to get it to pretend to be a human being. So the only way you can stop it is like throw the whole thing out. By its nature, it is a human imitator. That's what it is. That's how it's created. That's what it does. So saying, oh, well, we'll just tamp down the human imitation, right? That's ridiculous because that's what it is. So I suspect, and some other people that I talk to agree with this, that governments are not going to act, and because they're too afraid of the industry lobby, and the industry lobby will always say, oh yeah, regulation stifles innovation. And so they will only act if there is a significant catastrophe. And, I've spoken to one CEO of a major AI company who says a Chernobyl scale disaster is his best case. That is what he's hoping for, meaning the deaths of millions of people and, Chernobyl, economic impact of about $1 trillion. So something on that scale would probably get governments to act. And he thinks that's the best case.
Wouldn't it be too late then?
Well, if it's only a Chernobyl scale disaster, then the governments really clamp down and the companies. I mean, what has to happen is the companies need to figure out how to make safe AI systems, and they haven't. And the only thing that's going to make them is governments forcing them to. So yes, Chernobyl style disaster would be terrible, but at least then the governments would act. So how we make sure it's only a Chernobyl scale disaster, I don't know, right? I mean, it could be a Chernobyl scale or it could be a global catastrophe, right? The end of human civilization. If it's an engineered pandemic, maybe only 90% of the global population dies. And I guess we have to be grateful for small mercies. But I think governments have to face up to this choice. They can't ignore the fact that the biggest technology project in the history of the human race is underway, and they can't pretend to be 100% sure that that project will fail.
So let's talk about the work you are doing at Center for Human Compatible AI. What is your definition of human compatible AI, and what does that vision look like for 2030?
So the name of the Center for Human Compatible AI, is sort of it's a little dig at my colleagues who are making AI that is not compatible with human existence, right? So we would like AI that's compatible with human existence. And the approach we're taking goes under the heading of assistance games. So what does that mean? So the AI system's only objective should be to further human interests. And the key point about assistance games is that the AI system does not begin knowing what those human interests are. And this approach has some very nice properties. First of all, it avoids a classical failure mode of AI systems that we've been aware of for a long time. In fact, we've been aware of it for thousands of years. We call it the King Midas problem, because King Midas specified his objective: everything I touch should turn to gold. And then, of course, he finds that he can't eat anything because as soon as he picks it up, it turns to gold. And he can't drink anything because as soon as it touches his lips, it turns to gold. And he touches his daughter, I think, and then she turns to gold. And so it was a catastrophe because it was a misspecified objective. And for a long time, that was how we designed AI systems. They were machinery for achieving objectives that we plugged into them. Like, okay, win at chess or find the shortest path to the airport, right? And then off it goes.
Narrow.
So yeah, narrow, but a specific predefined objective. And if that predefined objective is misspecified, then of course you're in conflict with that system, because now it's pursuing an objective that's actually in conflict with what you want. And this is, I think, how most people have thought about the human extinction risk, is AI systems pursuing objectives that are misaligned with our interests. And because they're more capable than we are, they will prevent us from interfering. And in fact, they may decide that we are such a nuisance to the pursuit of the objective that it should get rid of us. And that's the only way they can achieve this objective. Because the harder we try to stop it, the more of a threat we are to its success, right? And so we actually give it an incentive to get rid of us. And so what the situation we have now with these large language models is they have a ton of these human-like objectives, but we don't even know what they are. So we're in a worse situation. They're pursuing objectives, but we didn't even specify them, right? They just absorbed them from the training. And so that's worse. And so these assistance game solvers, they have to further human interest. They start out not knowing what those human interests are. And so that has several nice consequences. One is that they behave carefully because they know that we may have objectives that they don't know about. And so they don't want to mess with the parts of the world where they're not sure how we want those parts to be. And so if we ask them to tidy up the table, they'll do it without knocking over the furniture or the vases or breaking the electrical cables or anything else. They don't want to violate our objectives, whatever they might be. So they're careful. They defer to human instructions by and large, because those instructions, you should think of them not as instructions per se, but as information that the AI system can use to update its beliefs about what humans want. So for example, if the human says, I want a cup of coffee, that's a useful update. But it doesn't mean that getting a cup of coffee is now the exclusive life mission of the AI system, right? That it should be done at all costs, even if that means traveling 500 miles across the desert to the nearest coffee shop and traveling 500 miles back with a desiccated cup of coffee, right? If there's no coffee around, it's quite reasonable, or the coffee's too expensive, it's quite reasonable to say, well, I can get you a cup of tea, or, how about a can of Coke, or, something else. This approach to building AI systems, I think the most important property from the point of view of safety is that we can prove, and we actually have a paper, it's called the off-switch game, that an AI system built this way has a positive incentive to allow itself to be switched off. So the system that's pursuing the fixed objective, like, okay, I have to get a cup of coffee for this, for the human, this is my life's mission, right? That system does not want to be switched off, because if you switch it off, it can't fetch the coffee. So these traditional systems resist being switched off, whereas assistance game solvers say, well, I might be doing something that the human doesn't like. I don't know what it is, but whatever it is, I want to avoid doing it. And being switched off will prevent me from doing the thing that the human doesn't want. And so I'm happy to be switched off if that's what the human wants to do. Now, there are some wrinkles in this story. So if the machine in question is a self-driving car and the human in question is the 2-year-old passenger who hears the ice cream van and says in the middle of the street, well, maybe it's okay for the car to override that and say, well, you're only a 2-year-old, you don't understand that that's extremely dangerous, and we don't stop in the middle of the street to get ice cream. And that's all can all be encompassed within the general theoretical framework. But I think this property of assistance game solvers, that they will allow themselves to be switched off, is pretty robust and will persist even as we elaborate the theoretical framework and move it towards real world systems and so on. So I think that's the underlying framework in which the center is operating. And we've been working on the theory, the algorithms. So how do you actually solve these assistance games? What about what about more difficult situations where, let's say, the human and the AI system have different perceptions of the environment? How does that work? What if there's parts of the environment that are not perceptible at all? Does that lead to additional failure modes and so on? So we can study these elaborations and show that, the basic safety properties persist, even as we make the framework more realistic. And then practical scaling up. So we've recently been able to show that we can make an assistance game solver that works in Minecraft. And it's in some sense, a pretty general purpose assistance game solver, right? So it's just observing the behavior of the human and figuring out what the human wants and then helping the human to achieve it. So I'm cautiously optimistic that this approach is really the right approach. In fact, it's the approach we should have taken to AI from the beginning, because that's what we want. And in fact, it's relatively easy to prove that if you have an assistance game solver that really does solve this problem for you, then you're better off, right? That's guaranteed to be beneficial to you, even if you don't even know what you yourself want. It's still going to be beneficial to you.
Thank you very much, Stuart, for joining our show. I'm sure
Right.
audience learned a lot from your insights.
I hope so.